Good evening, all the participants. I welcome you for the day 2, session 4 tutorial. And this tutorial will be taken care by Mr. Ankireddy Narendra, who is a research scholar working at Department of Electrical Engineering at NIT Rourkela. The speaker is going to deliver the session on an investigation of solar photovoltaic fed induction motor drive and its modeling by using the MATLAB. So I request Mr. Ankireddy Narendra to take over this session. So please, over to you.
Hello, good evening. Is it audible?
Yes, sir, it is audible. You can go ahead.
This is Narendra Ankireddy. I would like to deliver a tutorial session on the investigation of solar photovoltaic for induction motor drive. So, this is the basic outline of my presentation. A little bit of introduction and next coming to the application of PV, some basic application of PV we will discuss, and then what are the various converters we are going to use such that it will utilize to extract the maximum power from the PV, that is DC-DC converter. With the help of the DC-DC converter and as well as the MPPT algorithms, we can extract the maximum power from the PV system. So, and next coming to the why we are going for the AC motor for a PV, even though the power from the PV is a DC supply. So that is going to be discussed in the PV fed vector control induction motor. So again, in the AC motor, there are various types of AC motors. So we are focusing on induction motor. So again, in the induction motor also, there are various types of speed control techniques are also there. So for example, V/F control, direct arc control, and vector control. So why we are going for the, again we are chosen for the vector control is also discussed in the further slides. So in the PV fed vector control induction motor drive, generally we will have a PV panel and is supplied to the power to the boost converter to get the maximum power with the help of the MPPT technique, and that from the PV system is going to be changes according the insulation level, or it is called a irradiation level and temperature levels. So then the power is going to be changed, keep on changing. Then how it will affect the performance of the induction motor, and what are the other possible ways to manage the power balance between the PV and induction motor is also discussed. We will discuss some simulation result as well as the experimental part, how we performed that the PV fed vector control of induction motor is also seen in this further slides. So coming to the power generation, we are having most of the power generation from the coal and gas, means that is the fossil fuels we have dependent on more at current. So the not only the Indian government but also the entire world is looking to change toward this consumption of the fossil fuels. As we know that the recent trends also, the fossil fuel cost is going to increase widely. So and also it is going to be very difficult to get the fossil fuels. So in order to overcome the problem of fossil fuels as well as the demand of the current scenario, so people are moving toward the renewable energy sources. So if you see here, the estimation of 2040, the PV utilization is going to be, the generation from the PV utilization will be around 32% of the total power demand. So means the growth is going to be compared to here. Here the PV is up to 5% and it is going to increase to 32%. So means the drastic change in the power generation from the PV will encourage the researchers and industries to work toward the PV power supply. So what are the various applications of the PV power system? So we are already aware that some of the applications with the power generation of the PV is water pumping system, where we have much panels are connected and used for the pumping, water pumping application. So and also where the remote locations are there, though means where we cannot access the grid, there we can go for the PV power supply for the application of the electric power generation, where we can get in a remote residence. And also navigational aids means in some navigational system and telecommunication system. So where those are located in the far region from the grid, we can use those things for with the help of the power requirements of those things will be done with the help of the PV applications. Similarly, nowadays we are getting solar watches and solar calculators. So the power application using the solar is going to increase day by day drastically. So here we are focusing on the PV fed motor drive applications. So let me discuss what are the various possible ways that a PV power can be delivered to the drives. So here if you observe the PV power, so here where various colors are indicated such a way that the various alternatives can be done. So here the power transfer from the PV with the drives can be done in 4 ways. Those are if we have direct PV and fed to the DC motor. So as we know that the power from the PV system is a DC. So the whatever maybe the DC power is getting supplied to the DC motor. So whatever maybe the power is available, then the DC motor will on. If the PV power is not available, the DC motor is off. So second possibility is PV driven DC motor using a power conditioning unit. So here we much aware of that the losses in the PV panel is more. So in order to increase the efficiency of the PV panels, we are going to use that power conditioning unit, which is nothing but a DC-DC converter along with an MPPT. So here I have shown that in a red line path, if you observe, so the power from the PV is transferred to the DC-DC converter, and an MPPT algorithm is applied to that DC-DC converter. Then after achieving the maximum power, that is drive the DC motor. So similarly, third one is two-stage PV driven AC motor drive. So here AC drives can be driven with the help of the PV system. So where you have to convert that DC power from the PV system to the AC with the help of the inverter. So there are two possible ways to convert the DC power directly to the AC drive using a single inverter, or you can go for a two-stage system. So the green part, you will get the two-stage system of PV driven AC motor. First PV will generate the power, and then it is supplied to the DC-DC converter to extract the maximum power, and that extracted maximum power from the PV system is fed to an inverter. So then the inverter will use to drive the AC motor drives. So similarly, in a single stage system, it is in a violet color. The power from the PV panel is fed to the directly to the inverter instead of this DC-DC converter and MPPT. So which will reduce the cost of the converter system. So even though there will be a less power less power is achieved with the help of the PV system, in some application the reduction of the converter is more important than the cost of the converter reduction is more important than usage in getting the more power. So this violet path will show you the PV power will give the power transfer from directly to the inverter, where the inverter will give both the PWM as well as MPPT is applied with the help of the inverter. So means the MPPT concept is also included in the PWM itself. Whatever maybe the pulses we are giving to the inverter, those will take care of the MPPT as well as the control of the DC, the control of the AC drives. So direct driven again is classified into direct PV driven DC motor is again classified into two types. So one, we can directly fed the PV power to the DC motor, or with the help of the battery also we can fed to the DC motor. So means what is the advantage of using a battery is, so if there is a excess power from the PV system during the daytime, then that can be stored in a battery, and that power can be utilized later when there is no power available in the PV. So it's a PV driven DC motor with the help of the MPPT, means it's a with the power conditioning unit, we are having a PV system, and that power is transferred to the DC-DC converter, and there will be an MPPT to extract the maximum power from the PV, and then it is fed to the DC motor. So here, for the extraction of maximum power and the control of the PV system, we are using DC-DC converters, right? So the DC-DC converters is used for the optimal operation of the load with a negotiable cost and efficiency. So how we are choosing the right converter for different application? So we are having many DC-DC converters in a literature. How we can choose the best or optimum for this PV operation system? So these are the various types of the DC-DC converter: buck boost converter, chip converter, SEPIC converter, LEO converter. So resonant switching converter, super lift LEO converter, cascaded boost converter, like that many DC-DC converters are there. So people will get the dilemma to the selection of the DC-DC converter. So which DC-DC converter is suitable for the PV application? So the choice is also very important. So this choice of selection of the converter is depends upon the application where we are going to use that the PV, and also how much cost that can be incalculated with the in terms of DC-DC converter. So if you want go for the best performance, you have to give more input cost. So the cost of the converter circuit will increase, and you will get the better performance. In some application, you require a low cost converter such a way that you have to fulfill the remaining things. So means there we have to go for a low cost converter where we cannot afford the much cost in terms of the converter. So some application you require more efficient operation. So means then you have to go for the efficient DC-DC converter. So depending upon the application and requirements, what the industry is required or application is required, that will change the selection of the converter. So this is some basic circuit of the DC-DC buck converter. Generally, many PV application, either they will use the buck converter or a boost converter. So for simple understanding, I have given one DC-DC buck converter circuit and how the output voltage will vary according to the input. Similarly, the boost converter. Okay, what is the comparison between the buck and boost converter? You also know. Here the inductor will having the lesser values whereas the boost converter will have more value. So here the capacitor will be large and expensive, and it is less, and lesser one is sufficient. So switching rating. So in a buck converter we have high current rating, and in a boost converter low current rating. Additional blocking diode will serve the in both the circuits we require additional blocking diode which will restrict the PV current. So as we previously discussed, the selection of the DC-DC converter. The DC-DC converter has two tasks. One is it has to interface PV panel with the grid or drive, and operating point of the PV panel has to match with the MPPT. So the DC-DC converter has to perform the two operations. One is either it has to be integrated with the grid or to drive the motor at a operating point. So as we want to drive the motor, we have to go for the operating point. So we have to operate the PV panel such that match with the load line with the operating point, as well as it has to meet the maximum. It is also track the maximum power. So the choice of DC converter varies according to the cost, efficiency, and reliability, and the converter selection will depend upon the application. So coming to the PV fed vector control induction motor. So as we are mainly focusing on this part of the session, so here I have given the block diagram. So it's a simple diagram where we are having a PV panel, and the power from the PV panel is fed to the boost converter. So as we know that the boost converter is the combination of the inductor and a switch and a diode. So here there will be an MPPT algorithm. So it will take the input of IPV and VPV according to the value of PV current. IPV is nothing but the PV output current and VPV is the PV output voltage. So according to these values of current and voltages of the PV system, so the MPPT algorithm will keep on tracks at what value of VPV and IPV we are getting the maximum power. So that value is given to in terms of a duty cycle to this boost converter switch. So according to the duty cycle, so the converter circuit will on and off such a way that it will give the power of a maximum power. So that maximum PV power is fed to the two-level inverter. Two-level inverter having a 6 switches. So as we know that the inverter is used to control the induction motor drive also. So how we are going to control the induction motor with the help of the vector control, which is also called as a field oriented control. So how we can represent a PV cell? So as we know that the PV cell IV characteristics are shown in this figure. So if you go for the PV characteristics, so if you draw this I versus V curve of a PV cell, you will get the characteristics like this. So these characteristics are similar to the diode characteristics. So if you observe the VI characteristics of a diode, it is similar to the diode characteristics. Hence, the PV equivalent circuit can be represented with a current source with a single diode model. So here some of the equations and some of the shunt resistance and series resistance are added. So these are due to, if you observe here, so the shunt resistance due to the leakage across the PN junction and crystal defects, spin holes, impurity participant. So in order to compensate the losses due to this leakage of the PN junction around the edge and crystal defects, so we have taken the value in terms of RSH, which is also called as a shunt resistance. Similarly, this RS series resistance due to the bulk resistance of semiconductor and metal electrodes and contact resistance between the semiconductor. In order to overcome the losses of the semiconductor material, so we have taken that the losses in terms of the RS. So this is the entire equivalent circuit of a single diode model of a PV array. So these are some equations associated with the PV cell equivalent model. So as you've seen here, this IPV, the power, the current from the PV is transferred via diode as well as the output. So according to the KCL, I is equal to IPV minus ID. So whereas the diode current is can be expressed in terms of the charge, voltage, and temperature like this. So similarly, we can further expand this. Here, the combination of this the losses due to the RS.
I am with you, sir. I am agree with you.
प्रोफेसर आते ही यार
मेरा पीपीटी तो है नहीं यार, तीन ही है.
बस बहुत अच्छा
सगळं चांगलं बनत झालं.
Hello.
We request the participants to please be in mute.
Okay, first two equations are the ideal conditions of the PV system. So rest of the equations are related to the non-ideal condition where we have considered the losses due to the series resistance and shunt resistance. So similarly, this current depends upon temperature, and according to the temperature, also how the saturation current is going to change. These equations will represent. So based on these equations, you can model the MATLAB simulation of PV in terms of the single diode model. So these equations are very helpful for us in designing of the PV simulations using a mathematical modeling. If you want to design a PV cell in terms of a mathematical modeling, these equations can be used, and adding these equations one by one, and you will get the output characteristics of the PV system. So these are what are the terminology we have used in the previous equations are given here. So after the PV cell, we have fed that power to the boost converter. So here the basics of how this boost converter will on and off. I think all of you know the operation of the boost converter. So I quickly pass on through this one. So when the switch is closed for for a dt time seconds, then the inductor will get charged and more. This entire VPV will go to this inductor and will charge. So and during the open position, it will give the voltage across the inductor plus VPV as an output. So next, we are using a MPPT technique for the getting maximum power. So here the basic concept. So how the maximum power can be extracted from the PV system is disclosed with the help of a simple PV characteristics. So these are the PV characteristics of a solar cell. So if you observe this PV characteristics, so the power output given from the PV is going to be keep on increasing for a certain level. Once it reaches to the maximum value, then it will comes to the zero. So means we have to track the point. So we have to achieve this point, right? So where we can get the maximum power. So once the PV characteristics line reaches to this point, we have to log that point is nothing but the maximum power. So here this is normal condition. When there is a partial shading condition, so the regular methods are failed to track the maximum power. So partial shading condition means some shadowing effects will be there like that. Then we have to go for the, in order to track the maximum power of global maximum power in the partial shading condition, there is a problem of local maximum and global maximum. So means while tracking the line, we will get a maximum power at a starting point, but it is not a original maximum power point. It is a local maximum power point. So in order to track the global maximum power point, so you have to further track the line. For that one, so incremental conductance method is used to track the global maximum. So finally, at this point of maximum power, the rate of change of dP with respect to voltage is zero. So as we know that the maximum minima for the maximum minima for maximum minima, the df any function f of x, in order to find out the maximum minimum, we are going to do first differentiation is equal to 0. So similarly here also for getting the maximum power dp by dv is equal to 0. So here we have used for the incremental conductance method. So this is the flow chart how we are implementing the maximum power point with the help of the incremental conductance. As we have discussed previously, so in order to get the maximum power, the rate of change of power with respect to voltage has to be 0, right? So the power PV output power from is also given with the help of the V into I. So where V is the PV output voltage and I is the PV output current. So then I will go for a differentiation. I will get I plus V into di by dV is equal to 0. So this di by dV is nothing but change of current with respect to the change of voltage. So finally at maximum power point, so the I by V means what? Conductance, right? I by V means conductance. So the conductance value, the rate of change of conductance is must be balanced with the negative of the conductance value at MPP. So if it is greater than then the MPP point will lies on the left side. If it is less than this incremental conductance, then it will lies on the right side of the. So the rest of thing according to this change in MPPT, for example, if we find out this balance between the incremental conductance and conductance, then we need not to change any duty ratio as this. So else the duty ratio has to be changed in such a way that we will get the maximum power. So these are some equations associated with the boost selection of the converter circuit design. So how much boost value, inductance value, how much we have taken. We get it from the reference papers. So the maximum voltage into duty ratio, where A is the duty ratio and Fs is the switching frequency and delta I is the ripple current. So based on those values, we will get the inductance value, and also there will be a selection of DC link voltage. After the DC-DC converter, there will be a capacitor, right? So we have seen in previously. So how much voltage has to be maintained in order to operate that DC link voltage such a way that we will get the 415 volt line to line voltage across the induction motor. So this is the formula to calculate this DC link voltage. Similarly the rest of the things. So until now we have discussed the PV modeling as well as the DC-DC converter and MPPT. So once this part is done, we have to feed this entire power to the 3-phase 2-level inverter. So this 3-phase inverter basic circuit I have given here. So here the gate pulses are achieved with the help of the FOC and SVM. So why I have to choose an SVM is, so you already know, aware of there are various types of pulse width modulation techniques are there. So in which the basic problems associated with the sinusoidal PWM and those things are already discussed in the yesterday session, I hope. So the SPWM has both the advantages of third harmonic injection. If you are aware of the third harmonic injection, in a third harmonic injection, so the value of K times of third harmonic has to be injected to get the better operation of the inverter. So the value of how much product that can be multiplied with the third harmonic value. For example, we have K into sine of 3 omega t, we are multiplying means. So in a third harmonic injection, we are going to use the fundamental, okay, fundamental plus third harmonic component, right? So the value of K, so depending upon the value of K, the performance of the third harmonic injection is going to change. So here for a one value of K, you are getting one advantages, and one value of K, you are getting another advantage. So in order to achieve both the attributes of the third harmonic injection, the SPPWM concept has came. So here the SPPWM phase vector modulation. So here, as you know, that there will be 8 vectors, in which 2 vectors are 0 vector and one is active V7 active vector, and remaining vectors are enter cubical plane. So for example, if you are comparing if the reference signal is in the sector 1, so then there will be switches will on 0, 1, 2 and 7. There are the 4 possible ways to turn on this, achieve this V reference. How can I achieve this V reference? So in order to get this V reference, I have to turn on a V0 per a particular time, and V1 per a particular time, and V2 particular time, and V7 particular time, in such a combination that it has to give the value of the V reference at an angle of theta. So let us assume that this 0 vector will operate on a T0, and V1 vector will operate on a T1 time, and V2 will operate on T2 time, and V7 will on at a T7 time. So based on those things and also transformation, you will get the values of V1 and V2 for T1 and T2. Once you know the value of T1 and T2, then you can turn on this V0, V1, V2, V7 such a way that it will give the V reference. For example, if the V reference has to be shifted to next point, so then again what will happen? The theta value will change. Then accordingly, the value of T1, T0, T1, T7, everything will change. For example, if the V reference is transformed into sector 2, then again the switching vectors again is going to change. So 2, 3, 7, these 4 switches will on. So again you have to calculate what is the value of theta. So according to the value of theta and V reference, you have to again calculate the time period such a way that to get the reference vector. So coming to the various speed control techniques of the induction motor. So as we previously discussed, the way all we are known that the various available speed control techniques are V by F control is the basic voltage to frequency control. So where the speed of the induction motor is going to be controlled based upon the V by F. So here the main issue is the flux of the induction motor is proportional to the V by F. So in order to maintain the flux of the induction motor, so we keep on maintaining this value of constant. Means if you increase the voltage, then again we have to increase the frequency such a way that the entire flux of the induction motor has to be maintained constant. So these will have the scalar. This is also called as a scalar control. So here we cannot make the entire control operation very successfully. So then there will be another method which is called as a direct torque control method. So even though this is also it has some advantages and also disadvantages. So the major disadvantages of this direct torque control is high high current and torque ripple as well as the variable switching frequency. Here the direct torque control, the controlling of the induction motors or controlling of the inverter will be done with the help of the switching on and off, right? So whatever may be the control is performed using the inverter is done with the help of the turn on turn off of the inverter. So the turn on turn off of this switching can be done in a direct torque control using the variable frequency behavior will achieve. So with this variable behavior will gives you the concept of designing a filter will be difficult and the problem associated with the cost of the filter is also varies. Hence, these are the some of the drawbacks of direct torque control, and also it has high noise at a low speed and lack of direct control. So in order to overcome these problems, this field-oriented control is also called as a vector control. So this vector control comes into the picture. So where you can control the speed of the induction motor independently. So here the field-oriented control. So this is the block diagram of three-phase induction motor using field-oriented control. So here you are having the flux ripple, flux reference as well as the speed reference. So once if you supply the DC voltage to the inverter module, so that inverter module will give the AC. So here I have taken VD, you can take it as a PV power also. So with the help of the DC-DC converter, and we can fed to this inverter. So if you give the PV power by using DC-DC converter, that is fed to the induction motor. Once the induction motor is driven, we have to check whether the induction motor is achieved the desired speed or not. So then with the help of the speed sensor, we are going to get how much speed is there that is running at the induction motor. Once we compare with the reference value, so then we can achieve the ISQ. Similarly, the flux is compared with the help of the flux estimator and how much motor is operating at what flux is nothing but the psi r. So which is compared with the reference flux, and then we achieve the direct stator current of reference direct current. Once we transform this entire signals into voltage value, so we can achieve the reference Vs. So this reference Vs is nothing but the reference Vr. So what we have discussed previously, Vr in a SPM. So this Vs is nothing but Vr at an angle of theta. So once we know the value of Vr at an angle of theta, we can determine which sector it is coming. So according to that sector, we can calculate the values of T0, T1, T2 and T7. Then again that corresponding switches will on and off with the help of the SPM. So that SPM will gives you, so according to the value of reference voltage and angle, so the SPM block will generate the gate pulses. So that gate pulses is given to the inverter, and then the induction motor will run at a desired speed. So if you want to change the speed or torque or anything, then again you have to change the reference speed. Then again it will continue keep on moving on the closed loop system. So for example, I would like to show here how the field oriented control is done at a constant. Let us assume that the PV is working at 1000 watts per meter square. So means it will nothing but it will acting as a DC source, right? So it will give a constant DC voltage and constant current. So first I would like to consider the constant concept and then we will go for the variable concept. For example, if I consider this constant value, let me show the simulation part. Yes, it is visible. Karthik sir, is it visible MATLAB simulation?
Yes, it is visible. It is visible.
Okay, okay, sir. So I have designed everything in terms of mathematical modeling. Means you can done the simulation two ways, right? So you can get the simulink model, or else you can done with the help of the mathematical modeling. So I have done many most of the things in terms of the mathematical modeling. So if you observe this vector control block, I have designed the entire thing. I have taken the reference speed and IABC and what is the speed generated by the induction motor. Then according these currents and reference speed and those things, I have generated the gate signals to the inverter. Here also inverter also you can take it directly from a Simulink block. So where you can get the direct inverter, or else you can design this inverter also in terms of mathematical modeling. I have done everything in a mathematical modeling, that's why it is showing like this. So if you enter into the vector control block diagram, so here if you see here, so the reference speed and generated speed is compared with the speed control, which will produce the torque. Okay, this torque and reference values of gives the IQ current. Similarly, from the flux concept to what we have discussed in the block diagram, it will use the ID current. So once we know this ID and IQ, we can generate the reference values of VDS and VQS. So once you get the VDS and VQS, you can get the V reference. So I have also transformed this VDS and VQS in terms of the VR at an angle of theta. So which is nothing but the reference voltage at an angle of theta. Once you get this reference voltage and theta, which is fed to the space vector modulation technique. So I also you can apply this SVPWM two ways. So either you can go for the normal comparison between the various signals and you can generate the SVPWM, or you can write a MATLAB program such a way that you will get the pulses. So I have written a MATLAB program to get the SVPWM technique. So this entire block will MATLAB function which consisting of a program to determine the whatever may be the pulses I required, SA, SB, SC according to this reference vector value. So reference voltage vector, they will produce the three pulses. So I have taken only three pulses and rest will be complementary. As we know that once we know the SA and SB, SC, so one leg we know, then other will be complementary. So the three switches is given to the inverter module. So this inverter module will use the whatever may be the VAN, VBN, VCN. So that inverter will give this VAN, VBN, VCN. So which is fed to the induction motor. Again, induction motor is also you can get directly from the Simulink library, or you can write a mathematical modeling based system. So I have taken mathematical modeling system for VA, VB, VCN. This is load torque. So if you want to change the load torque also you can give externally with the help of the TL. So once this values is given to the induction motor, inside this one we are having a mathematical modeling equation. So you will get this IA, IB, IC values corresponding to the induction motor and the electromagnetic torque as well as the speed. So as we have to see this how the value of current and torque and these things. So I already run the simulation and I already given here. So let me go to the slides. I will show the results. So these are the ratings what the induction motor we have taken. The poles are 4 poles and speed is 1400 RPM, 4 kilowatt, 50 Hz. So these are the some ratings of this induction motor. So in the further session, we are also discuss how these parameters extraction in a experimental way also we are going to discuss soon. So here I get the initial starting current will be high, as you know that the induction motor will give you high starting currents. So at the starting we are getting high currents. Once there will be a settling of the torque and the reference speed is achieved, so then it is going to be settled. So the torque is going to be zero once the reference speed is attained by the induction motor. So the currents are going to be settled as well as the induction motor speed is settled and the torque is going to be stabilized. So again here I have taken a torque external load. I have applied a load of certain Newton meter. Some Newton meter I have applied here. Then there will be again a current increase when there will be a load means. So if a load will be fell on the induction motor means it will drive it will draw the more current, right? So it will again draw the more current, and there will be a slight changes in the speed during this condition. So once again it will settle into the steady state. So if you want to operate the induction motor in a reverse direction, then I have given a negative torque. So then there will be a reference speed of minus 1200 RPM I have given in a simulation. Then once until unless it will reaches to the reverse reference speed, the torque is going to be negative and the currents are also going to be negative. Once it reaches to the reference value, then again the current and everything is going to be settled. So again I have moved that reverse operation to the forward operation, then it will again it stabilize into rated speed and again it will changes accordingly. So these are the settling time and how much time is taken to reach the steady state value. So these table will gives you the values of different modes. At starting condition, how much settling time is required for a induction motor, as well as the when I applied a step load of 9 Newton meter and again I removed that load, then how much time is required to transfer. Again speed for I have applied a speed reversal direction, right? The motor speed has to be driven in the negative direction as well as again from a reversal to the backward to the normal direction. So these are the some parameters we achieved in the simulation. So this is the condition only when there is a constant situation. For example, generally the PV power is not going to be constant, right? So the power from the PV system is going to vary. Then how we can go for to drive the induction motor when there is a variable power, right? So this is the variable irradiation condition. So there is a possibility such a way that we can get the variable power drive motor. So here the power from the PV system is going to be variable. Hence, the speed of the motor is going to be changed such a way that it has to balance with the output power. So means what? As we know that the power of the induction motor is nothing but the torque into omega, right? So if you want the input power is balanced with the output power means what? Either you have to change the torque or speed. So if the speed is changed accordingly the power, then it will be balanced, right? So here we have taken a concept of the variable speed induction motor drive, which is helpful in the water pumping application most probably. So here I have taken a PV system with a boost converter. Okay, this boost converter, as we know that to use DC-DC converter to get the maximum power, and there will be a three-phase two-level inverter and which is driven the induction motor. So here we are sensing this IR, IY, IB, and in a real-time operation, so we need a controller such a way that to get the closed loop operation. So this can be done with the help of the in order to get the pulses to the SPM, in order to give the pulses to the inverter module, we have to have a real-time interface unit. So that may be an Arduino or a FPGA or DSP programming or DSpace. So here for my application, I have taken a DSpace 1104. So where we are having a DAC and ADC switch, ADC blocks to transfer this analog into digital as well as the controller part in a digital that we are going to discuss in sooner. So if you observe here, the speed is sensed back as well as the currents are sensed back, and the DC link voltage is also sensed back. So based on these values, the control part will run. And here, if you observe here, the speed of the induction motor is changed in such a way that to balance the DC link voltage. So in order to better operation of the induction motor drive, the VD must be maintained constant, right? So if the input voltage fed to the induction motor has to be constant, means the value of VD must be constant. This can be achieved with the help of the voltage control loop, which is given here. So this is the sum of the simulation results we have performed at various variable irradiation conditions. For example, at initially it is operating at a 600 watts per meter square. So the IP current is start increasing. So initially it will take some little bit of time to attain the maximum value, which can be achieved with the help of the that corresponding irradiation. Once it reaches to the value, and it will continues to maintain that constant value. So here the voltage from the PV panel is going to be constant. Similarly, with the help of the controller, we have maintained the VD of the DC link voltage is constant. So here, if you observe these currents also, at starting we are having induction motor having high current, then it will give the high current. Once it will be settled, then it will give the steady state value. So here the torque, initially the torque is also high due to the starting torque will be high of induction motor. Once it reaches to the steady value, and it will maintain a constant value. So this load torque, here we have considered a load torque of a pump load condition. So where you know that the pump load condition having proportional to the load torque is proportional to the square of the speed. So TL is nothing but the K into omega square. So here the corresponding speed is achieved at a 1300 RPM. So this is the only for a starting condition of 600 watts per meter square. These are the results we have got. Similarly, for example, variable irradiation is nothing but the irradiation is going to be changed. For example, we have created an irradiation change of 100 watts per meter square, means 600 to 500 at T is equal to 1.5 seconds. So if the irradiation is going to be changed from 600 to 500, then if you observe the current of the PV panel, so maintaining the constant PV BP, so constant voltage, such a way that the current is going to be changed to balance the power drop in a PV. So as we know that the irradiation change is nothing but a power change. Irradiation change means the solar will give the less power. So here the current will drop. So the voltage as usually we are keeping constant, and only the current will change. So similarly, here if you observe here at 1.5 second, the IR, IY, the three phase currents are going to be decreased. So means what? Here, as we know that the IP value is keep on changing, means in order to make the power balance, the current in fed to the induction motor is going to change. The currents are going to change. Then again at 1.5 there will be a sudden changes in the irradiation, means sudden change in the power is taken place, means the electromagnetic torque will drop little bit and again will settle. So here due to change in the irradiation level, the load torque is changed. Why the load torque is changed means as we know that the pump load TL is equal to K into omega square. So as the speed of the induction motor will drop, as the input power will change, means as we discussed previously, the speed of the induction motor will drop. So the speed of the induction motor will drop means what? The load torque will also drop. So if you observe here also the speed is fall at a level from 1300 to 1250 RPM at T is equal to 1.5 seconds. Similarly, if there is a possibility of increasing irradiation is also there, right? So there is a two ways of possibility, either it will be a constant irradiation, or it will be a decreasing irradiation, or it will be increasing irradiation. So previously we have seen the constant as well as the, now we are going to see if there is an increase in the irradiation level from 400 to 600, then how it will react. So here the PV current is going to increase, right? So as the voltage is going to be constant and VD is going to be constant. So if you observe the IR, IY, IB, and these three phase currents are going to be increased as the irradiance increase. So again, this torque will rises sharply due to the change in the power and again settles to a steady state value. So similarly, the speed of the induction motor will attain previously increasing. So from low value to the high value of 1300. So here the low torque will increase as the speed increases means the low torque will increase. So this is the experimental setup how we performed this entire experiment. Here we have taken the DC programmable power supply to compensate the PV system. So which is given to power to the this boost DC-DC converter, and after this DC-DC converter that is fed to the three-phase two-level inverter. So with the help of this D space, we have given the pulses to this three-phase two-level inverter, and which is fed to the induction motor drive. So again the feedback is given to the D space, and then we get the desired pulses. So this is DSO we will get, and we have taken a resistive load to compensate this generator output. So experimental setup what we have discussed previously will consisting of various parts. So generally we can perform this PV fed induction motor operation either with the help of the PV panels as we see here. So but we have to connect the many panels in series, and the cost of the panels will be more, and also in a real time it is a better option to go for this operation. So as per the lab point of view, we have taken the similar operation of this PV panel can be performed with the help of the programmable DC power supply. So this programmable DC power supply, how it will work, we'll discuss in the next slides. So there are four possible ways of interface this PV programmable DC supply with the PC. So these are the four options of communications are there. General purpose interface first we can go for RS-232 communication system or USB connection or LAN connection. Means you can connect this programmable DC power supply. So this programmable DC supply with this PC in these four formats. So we have taken only USB format, and there is an option you can connect any of these four. So these are the some basic software and hardware requirements to install this DC programmable power supply. So if anyone interested to go for the DC power programmable power supply, so these are the basic requirement for this installation of that system. So once you install the every software, you will get this display like this. So here I am explaining this one how it will use the DC PV equivalent power or PV equivalent characteristics. I would like to show you. So for that one, I am showing these things. So once you have done everything, and it will show this startup like this. So there you can scan for this communication part in which way you have to convert. And again here you are having a device number. So this programmable DC power supply will have can be connected up to 10 number. So you can select which number you are connected, which channel you have connected the system, that you have to highlight this part. So once you have connected which medium of interface, it will show the arrow like this. So if it is connected to RS-232C, it will show if it show here. Similarly, LAN also, and also the device number at which you are connected. So once you have done everything, this main panel display will be like this. So if you observe this here, one is highlighted means you are connected a system with a input of 1. So this highlighted path will show you the corresponding values of the device 1. So here you can give the VI values with various types of inputs you can give. Either you can give using a MS file or Excel file, or randomly you can give some values here, or data sheet you can get from the data sheet also you can give the values. So based on those values you will get this characteristics of PV. So if you want to incalculate partial shading condition also, here there is an option for you. If you observe here, so this percentage will indicate you how much partial shading effect will be there. So means 100% means if you want to give 100% irradiation value means, for example, if you want to go for 1000 watts per meter square in a standard way, so you will give on of it 100%. So if you want to go for a 750 watts per meter square, then you have to turn on this 75%. Like this, you have to can perform this partial shading condition. So once you have done everything, then you can run this program and you will get the desired PV characteristics as an output. So then I would like to explain whatever the interface is there here for an inverter module. So we have used DSpace 1104. So if you seen here, we are having an ADC channel and DAC channel. So as we know that the output from the induction motor is analog signal. So but the controller what we are going to design is a digital controller. So again we have to transform that analog signal into digital signal. So that can be done using this ADC channel. So with the help of the ADC channel, we can transform that analog signal into digital signal, and the controller will get control values, and that will be given in terms of digital, right? So the control signal will be given in digital values. So again, that division, that digital value has to be given to the real-time system in an analog manner. That can be done with the help of the DAC. So here the DSpace will provide both the ADC channel and DAC channel. Here DAC channel is there and ADC channel is there. If you want to give the number of signals to this one, and again it can be transformed and given back to the system. So or else you can use this master slave operation also. Here also you will having analog and digital. So once you install this DSpace model, you will get a, once you click on this model, you will get like this. So you can select which DSpace model you have installed in the system and interface it, then you can select. Here I have used 1104. So once this display will be on and I can click on this one, so I will get into the platform of the DSpace 1104. So this is the files I can extract, whatever may be the files I require to control the signals, and we can get from this DSpace RTI 1104. So here I have used the inverter, semicron inverter stock. So these are the basic components we are having in the inverter. So this inverter stack can be operated, okay, as you know that the inverter means what? That can be converted into DC power into AC power. So in some application, if there is an AC power is available, that can be rectified, and that rectified power is given to this inverter stack, and which will give the inverter output. Or otherwise, if you are having a DC supply, you can directly give this DC supply to this DC bus and you will get the required inverter output. So here there will be a gate driver circuit, means you have to supply the gate signals to this and this and this. Once you give the gate signal such a way that the inverter will on and off. So before giving this semicron inverter, so there one auxiliary circuit is required. That auxiliary circuit we have given here. So whatever may be the pulses from the controller is nothing but the 5 volt pulses we are getting from a digital signal. So but whereas this semicron inverter will operate at a 15 volts level only. So in order to step up this, we are going to use CD4504 for transforming this 5 volts to 15 volts. So whereas this intermediate circuit is nothing but an isolation circuit. So generally we are having an isolation circuit inside of the semicron module, but in order to little bit precautionary way, we can also connect an isolator opto isolation circuit. Okay, opto isolation circuit which can be achieved with the help of the HCPL2602. So HCL is because the output from this is nothing but inverted output. Again, in order to get the normal output, we have connected to. You can also use only single one also. You can also single one you can use, and the inverted output is given to the lower leg and normal output is given to the upper leg also. You can do it. So even though if you are not using this, also not at all a big issue for this inverter stack. For the sake of only isolation and little bit safety, we have used this one. Or else you can directly give that 5 volts supply to this CD4504. You will get the 15 volts signal, and which will fed to the inverter module. So in order to perform this PV fed induction motor drive, so before going to start the experiment, we have to extract the various parameters inside the induction motor. So the basic problem of identification, electrical parameters and mechanical parameters are there for induction motor. So electrical parameters, as we know that we can measure is in the no load test and block load tester, as we already aware of that one. Whereas these mechanical parameters of moment of inertia and friction coefficient are has to be achieved before perform the induction motor. As we must be aware of this, J and B are more crucial part in achieving the good speed response. So in order to achieve the good speed response, the value of J and B must be very accurate value. So how we can estimate this value? So there are various method of estimation, okay, retardation test and those things are also there. I am discussing some simple technique to determine the value of B and J. So here the B of electromagnetic torque is estimated using the rotor speed, and the inertia coefficient can be using curve fitting method. So that we discuss in the coming lecture. So how we can measure, for example, at no load condition, okay, at no load condition, the electromagnetic torque is equal to the frictional coefficient only. So then you can get the value of P by 2 is equal to MD by omega. So how I can achieve this MD? So you can achieve this MD value in terms of the I current values. So this current value, how can I achieve this current value? These current values you can achieve using this. Already we have seen the field oriented control where you can get this ISQ and IMR. So we there with the help of these values you can get this MD. So how can I get this L0? So that you can done with the help of the electrical parameter quantities from the no load and block rotor test. You can get this L0. Here P is the number of poles. So once you got this MD is known, and you can go, you know the poles, and if you know the starting speed of the induction motor, then you can achieve this B. So once you achieve this B value, you can go find out the moment of inertia of induction motor using a curve fitting method. So here we are, electrical parameters can be achieved with the help of the no load test and block load test. So here for this operation, we have already shown that some current and voltage sensor are also used to get the feedback signal. So we have used various types of current sensors. So here we can use, this is one current sensor. The LA55P, so it will sense the current up to 55 amperes. This is the basic current sensor diagram. So once it will sense the current, and it will compare, and it will give the output voltage. The current is given in terms of the output voltage. That's why here it is showing 1 volt is equal to 10 ampere. So you have to very much careful while taking care of this multiplication factor, because whatever may be the values you are getting from the current sensor is nothing but in terms of 1 volt means 10 ampere. Means, for example, if you are getting 2 volts means it is 20 amperes. So while in D-space modeling, you have to get the use this multiplication factor to balance the parameters values. Similarly, the voltage sensor. So here it will measure the voltage sensor with the help of this kind of sensors. Okay. So this is nothing but a potentiometer. If you give the auxiliary supply to this sensor, and it will sense the voltage. So again, we have reference speed estimation is there. So the speed estimation can be done using a speed encoder. So various types of encoders are there. So how this general principle of encoder is working principle of this encoder is shown here. So here once the motor is running means that this will give the digital values. So this digital values is transformed in terms of measured in terms of this RPM and degree of rotation, how much rotation it is done. Using based on these digital values, we are getting the value. So what are the various types of encoders? Optimal encoder is nothing but a encoder which will works on mostly on the lighter disk detector. So a linear encoder is used in industrial automation control. So absolute encoder in some application we required a specific means a precise value of speed. Then we will go for the absolute encoder. So it will be more costlier for this absolute encoder because it has more precision value. So again, incremental encoder is there. It will be most commonly used for different types of application where the speed is going to be keep on increasing based on the encoder. So previously we have shown the block diagram of variable irradiation condition we have taken, right? So that we have performed experimentally. So here we achieved some of the results have given here. So VP is the PV voltage and IP is the current. Once here the IP we start building up once it is settled to certain value. Here the value of VD is going to be constant. So with the help of the voltage controller loop, so again, initially the torque will be high and it will reach us to steady state value. So the load torque, once the motor is keep on starting, it will reach us to the torque EL, and at initial condition the motor is starting and then it is achieving the desired speed of NR. So here at a starting condition, as we know that the induction motor having high starting currents, it will having high starting current. Once it reaches to the speed of steady value and it is going to be constant. So here we have taken the condition of variable irradiation. Okay. So the voltage of PV is constant and the current output from the PV system is going to be decreases according to the value of the irradiation. So coming to this VD is going to be maintained keep on constant. So coming to the torque, so during the change in the irradiation there will be a dip. So and there will be a drop in the load torque and speed. Similarly, there will be a drop in the current. I have taken only per phase current, so hence there will be a drop in the current. Okay, once irradiation will be get decreasing, means the current will going to be decreased value and settles to a final value. Similarly, if I taken a increasing irradiation value, so the IP value is going to increase and VD is going to be constant. So there will be a slight increase in the torque and reaches to steady state value, and TL value is going to be increases as the torque load torque it depends upon the speed. So the irradiation increase means the speed is going to be increased, and during the changes there will be a certain distortion of the current, and again it will be increased current values of per phase IR and settles to a certain steady state values. So in this entire session, we have presented various utilization of solar power and how we perform the PV fed vector control induction motor and some experimental aspects at a variable irradiation condition, and those things we have discussed. Thank you. If you have any queries, you can ask.
The participants can unmute yourself and you can interact with the speaker if you are having any queries.
Good evening, sir. Regarding motor parameters estimation, in our lab we have a motor generator set, PMDC
Okay.
motor generator set. We are unable to measure the inductance of the motor. Is
That you can perform with the help of the load test now.
with load test?
Yes, yes.
Okay, sir.
Any more queries from other participants? There are no more queries. Thank you for presenting your model and explaining with the help of MATLAB, sir. I hope the participants got some knowledge after going through this tutorial session. Thank you once again. I think we can close the session, sir. You may leave the session.
Okay, thank you for giving this opportunity, and thanks for your entire patience for this entire session. Okay, thank you once again.
Thank you.
Thank you, Narendra. Thank you, Karthik. Okay, so it's a nice presentation, and I hope the participants also get some idea from your work. Okay, so today we are conclude our second day. Okay, of our SPC. So tomorrow morning again 9 a.m. again we'll start with our seventh session. Okay. So session 7 again it will be. I hope it is taken by Professor Krishna Roy. Am I right?
Yes, sir. Yes, sir. Yes, sir. Krishna Rai,
Yes.
sir.